In this video, we'll be discussing the latest results from models and simulations of our innovative hypersonic engine design. If you're not familiar with this, I'd recommend watching the two introductory videos on the engine first. I link these in the top right of the screen so that you can click on them and view them. I'll also link relevant papers in the description below, including the one with these results when it's published. The main problem with current hypersonic engines like scramjets is that the fuel and air doesn't mix properly. The air passes too quickly through the system and shockwave interactions between the two provide a barrier to their mixing. The result of this is unsatisfactory combustion, and this is the main issue with these engines and why they don't presently work. Our solution to this problem is to switch off the airflow through the engine duct, inject pelletized fuel, either solid pellets, liquid droplets, or gas capsules, or a combination of these, and then, as the fuel falls through the duct, switch the air back on. The air envelops the fuel pellets and the pellets then disintegrate, releasing their load evenly through the air, so facilitating complete combustion. This process is shown in the animation on the screen. One big advantage of this system is its flexibility. Not only can the pellets contain fuel, but also things not related to combustion, for example pyrophoric compounds or substances which help to ionize the air for other engine types. For this system to operate, two important parts not present in other propulsion systems need to be verified. One of these is the behavior of the fuel pellets in the flow. For the engine to work, they must be completely embedded in the airstream. The second part is the air switching system. This must be able to redirect the airstream efficiently without causing operational disruption. Let's consider these two issues one at a time. Firstly, the behavior of the pellets in the flow. In order to be sure that the pellets do embed properly, a four-fold simulation and modeling approach was adopted. These four approaches were: firstly, to simulate the pellets with computational fluid dynamics. Secondly, to model their dynamics using measured and published values of drag coefficient. Thirdly, to use calculated values of drag. And finally, to assume that all the airflow energy is placed across the pellet. This forces it forward. This final strategy is a backstop case. It is the worst possible theoretical outcome. Let's examine these one by one. Firstly, the pellets were modeled in CFD. This was done by simulating the pressure across the pellet as it speeds up, as shown on the screen. From this, we can calculate the force on the pellet and therefore its acceleration. This method is likely to be the most accurate, as it captures and incorporates the full Navier-Stokes model. A separate and independent 3D simulation and calculation were also done to confirm the results as shown. A second method is to use published values of supersonic drag coefficient. These have been published by NASA and various other organizations to calculate force, as shown on the screen. This can similarly be used to produce an acceleration profile for the pellet. Thirdly, some important elements of the drag can be calculated theoretically, for example the wave drag, and these can be used with empirical figures to produce an overall figure for drag. Finally, a worst-case scenario can be calculated. It would be literally impossible for the pellet to accelerate any faster than this. We can calculate the stagnation temperature as shown on the screen. And from this, the maximum flow velocity can be calculated from the formula shown, and this translated into an equivalent dynamic pressure. If we wanted to be even more extreme, then we could add in the static pressure, and this would be the equivalent of saying that there was a vacuum behind the pellet. The upshot of all this calculation, modeling and simulation is shown on the screen. it turns out that even in the very worst case scenarios, the pellets embed extremely well into the flow, in fact better than we had dared hope. Let's turn now to the second innovative system in the engine, the rotating nose cone. The nose cone itself consists of structures which are well researched, for example the pointed cone and the standard scramjet intake duct or inlet. This means that when it is not rotating, it has simple and well-established characteristics. The question is, what happens when it starts rotating? And does it disrupt the airflow in any way which would cause the engine to fail? We can analyze this situation by considering the area swept out by the edge of a duct during the passage of an air molecule through it as it rotates. This is shown in the diagram on the screen. One can see intuitively that if the duct moves only a small distance during the transit of an air molecule through the inlet, then the effect of rotation is minimal. There are two ways in which this rotation could affect the flow. The first is the virtual wedge swept out by the edge of a duct, and this will deflect air molecules into the body of a duct, which could cause an effect rather like an expansion fan emanating from the edge into the duct aperture. Secondly, the aperture is restricted as the duct turns, and there is a maximum restriction for normal operation. The restriction in aperture size required to produce engine unstart is given in scramjet references. When we follow the calculation through, the nose cone speeds for practically sized engines, allowing for a large factor of safety, turn out to be in the region of tens to hundreds of RPM. This in turn is good news, as it means that pellet injection densities and rates are very practical. The paper referenced in the description below gives details of this. In terms of particles deflected from the edge of a duct into the aperture, this is offset by the new area of a duct exposed at the other forward moving edge of a duct. However, both these factors indicate that a long duct moving as slowly as possible is best in terms of the duct behaving in a predictable way. In the next stage of the project, we need to verify these results in an experimental setting. This is fairly simple in terms of pellet dynamics, because they can be tested in a standard shock tunnel. The impinging gas in such a tunnel is very similar in nature to the oncoming stream from a rotating nose cone. The pellets can simply be dropped into the duct with an appropriate timing and their behavior in the stream filmed with a high-speed camera. Unfortunately, the nose cone is more difficult to verify in an experimental setting. Shock tunnels offer too short a blast of air to assess the effect of rotation, and very few facilities exist which are capable of generating longer bursts. The alternatives include testing in an energetic flow, for example from a rocket nozzle. Alternatively, it could be tested in a small sounding rocket if it were appropriately instrumented. In the meantime, more sophisticated simulations using moving grids would help to clarify the situation. One of the benefits of the system is that there is a clear step-by-step roadmap between the present research and a fully working engine. The first task is to confirm the behavior of the pellets and the nose cones, as we've just outlined. This means having a shock tunnel or similar equipment, and this would cost in the region of a couple of £100,000 to hire. If these basic concepts prove true, then it would be time to build a single-speed demonstrator version which could be mounted on a small sounding rocket. The price of this would probably be in the region of £500,000 to £1 million. The following stage, the design of a full prototype engine, would require the help of an aerospace company or organisation due to its complexity, cost and the facilities required.